Okay, in this video we are going to discuss another method to solve differential equation, and this method is called the linear differential equation. Right? First of all, what is the shape of the linear differential equation? The shape is this one. Derivative of y respect to x plus p of x times y equal to q of x. Alright? Now, the derivative of y respect to x should have always coefficient 1. I'm going to tell why we need this to be 1. But then the rest, it should be p of x. P of x could be anything as long as it is function of x, times y should be power 1, and then equal to q of x. Again, here this q of x is anything as long as it is a function of x. It cannot be y, but it should be something with an x. Alright, now this linear differential equation is called linear because the power of the y and the derivatives of y is 1, as you can see here. So that is why it's called linear differential equation. Alright, now on this video we are going to cover the basics of the linear differential equation and then how are we going to solve it. Okay, so first the coefficient must be 1. Okay, another thing is that p of x must be different than 0. Now, what if p of x is equal to 1? Now, what happens is equal to 0, sorry. What happens if it is equal to 0? What happens here is that the derivative of y respect to x plus 0y equal to q of x. So as you can see here, this is equal to 0. Okay, so what you have here is derivative of y respect to x equal to just q of x, and this is a variable separable differential equation that we can solve like in the previous method. So you can see here the differential y is equal to q of x, differential of x, and then you apply the integrals. Okay, so that is why we need p of x different than 0, because if it is equal to 0, then it becomes a variable separable differential equation. Okay, another thing that we need is that q of x must be also different than 0. Again, the question is, what if q of x is equal to 0? Okay, so what happens if this is equal to 0? So what you get is the derivative of y respect to x plus p of x y equal to 0, because we make q of x equal to 0. Just like in the previous, the problem becomes a variable separable differential equation. You can see here how it works as a variable separable. So differential of y respect to derivative of y respect to x equal to minus p of x y. And just pass this to the other side, and let's separate the variables. Differential of y over y, this y is a multiplication, and the differential of x as a multiplication, equal to minus p of x, differential of x. Okay, just for the sake of fun, let's solve this differential equation. So integrals on both sides. Okay, so on the left, what you get is the natural log of y equal to the minus the integral of p of x, differential of x, plus the constant. Okay, now, because we don't know what is p of x could be anything as long as it is function of x, therefore we cannot solve this integral, so we leave it like that. Okay, let's use exponentials on both sides, and that is to clear the y, because the exponential is opposite to the natural log, so it cancels. So what you get is the y equal to exponential of the minus integral of p of x, differential of x, plus the constant. And here let's use the properties of the power, or of the power, exponential of the minus integral of p of x, differential of x, times exponential of the constant. Okay, exponential of a constant is still a constant, so this is a constant. So the y here is going to be the constant exponential of the minus integral of p of x, differential of x. Now, this kind of solution is called the homogeneous solution. Homogeneous solution. Alright? And why it's called homogeneous? Well, it is called homogeneous when the linear differential equation is equal to 0. So that is why it is called homogeneous solution. But in the end, engineers, this is just a variable separable differential equation. So that is why on the linear differential equation, we need the p of x to be different than 0, the q of x different than 0, because they will become variable separable differential equations. So this is different than 0, this is different than 0, but here we need equal to 1. Okay? Now, let's keep this formula for later videos. And I'm going to tell you to remember this formula because it's going to show up later on the course, alright? Okay, on the next video, what I'm going to do is how to solve this kind of linear differential equations by using the integral factor. But because what we are going to try to do is this is definitely not a variable separable differential equation, but we are going to develop a method to convert this linear differential equation into variable separable differential equation. It's going to be very difficult, so that's why I need another video. See you.